This is joint work with Yang Wu, my advisor Andreas Hebelin, Wentao Zhou, and Buntao Lu. We all know that debugging networks can be difficult sometimes. Consider this example, where Bob is an admin of a software-defined network that looks like this. He would like certain requests to be routed to the server on the left. But he made a mistake in his controller program, and as a result, his network is misconfigured, and only the green packets were routed to the correct server, but the red packets were misrouted. So Bob might get a trouble ticket that asks him to fix his network. So what Bob needs is a good debugger. Existing debuggers can tell us what happened in the network. For instance, NetSite can produce a packet history. If you ask NetSite why there's a packet at switch C, it will tell you that it's because but as they go to the second hop, only the green packet was routed to the correct server, but the red packet was misrouted. As it traverses a different set of switches and gets matched against a different set of flow entries, it has a very different provenance tree afterwards. So what can we do about this? Next, I will describe a starting point for our algorithm, and then I will refine the algorithm in several iterations. To address the previous problem, we observed that provenance describes network execution. Therefore, our algorithm should pinpoint a couple of early differences in the execution and leave out the different consequences that came afterwards. So for this, we take a three-step approach. First, we conceptually roll back the execution to a divergence point. We then change the faulty node to the node on the correct tree, and then we roll forward the execution to align the trees. The benefit of this is that this identifies an initial difference but leaves out the large consequences. So how would this work? We will first roll back the faulty execution until we realize that the two packets were processed by different routing entries. For instance, here we see that the red packet was routed to switch C, but the green packet was routed to switch E. We would then make a change so that the two packets are routed similarly, and we would roll forward the execution to align the trees. To map this algorithm to the topology, remember that the scenario looks like this. What the algorithm does is to unwind those packets and make a change to the network so that the bug is removed, and test out the change by rolling forward the execution. This already goes a long way in identifying the initial differences, but not the consequences. However, there's still one problem. In the previous example, I've shown you a simplified provenance tree. But if you look closer, the provenance trees actually look like this. Remember that those two provenance trees are triggered by different packets. So we want that fact to be preserved in our algorithm. If we apply the algorithm directly to those provenance trees, it would actually identify the two packets to be different. Of course, the algorithm will change the red packet to the green packet, and when we roll forward the execution, the two trees will be identical. But this is not what we want. And our solution for this is to establish an equivalence to preserve the crucial differences between those provenance trees. So values on the trees could be identical, different, or they could be equivalent. And our goal is to make those trees equivalent, but not necessarily identical. Therefore, we arrive at the second refinement of our algorithm. We roll back the execution to a non-equivalent point. We then make a change to the faulty node so that it becomes equivalent to the correct version. We then roll forward the execution to align the trees. The benefit of this is that this can preserve the crucial differences between the trees. So how does the equivalence work? We will start with an initial equivalence relation between the packets. In this example, we would establish a mapping between packet fields that are different. For a more general approach, please refer to our paper for more details. And we would keep track of the mapping while we go up the tree. And as long as the trees are still equivalent, we would continue mapping until we arrive at a non-equivalent node. More generally, this requires a form of taint analysis, which works like this. Consider this example where you're computing packet-level statistics, and you have two instances of the computation. Suppose you know that the two packets are equivalent. How do you know whether or not the stats are equivalent? The idea is to use taint tracking. We would create a taint for each equivalent fields of the packet. For instance, here we have the destination port and the packet size. And we would look at the computation and see what it's doing. For instance, here we see that the port is simply copied to the stats. We would therefore do the same when we are propagating the taints to the parent vertices in the graph. And for the packet size, we would realize that it's multiplied by 8. We would therefore do the same for the green taints when we are propagating them from the child vertices to the parent vertices. This will allow us to recognize that the two parent vertices are also equivalent. We would repeat this process until we arrive at a non-equivalent node. Then we would stop and make the change. Back to our running example. Here we see that two equivalent packets are routed to different switches, so they are no longer equivalent. Now, two things could happen when we are trying to change the faulty node. It could be that the faulty node depends on some other nodes. And in this case, we would need to create their equivalents recursively. And it could also be that there's no dependent node anymore, in which case we would directly insert the equivalent version of the faulty node. And more generally, this requires propagating taints in the reverse direction, and I encourage you to read our paper for more detail. We're getting close to our final algorithm, but we still need to refine it one last time. The process I just described may only align part of the tree. The problem is that there could be more than one difference between the trees. For instance, in this example, only part of the trees are aligned. And the solution for this is to repeat the process until the trees are completely aligned. For instance, in this example, we would continue to go up the trees and make another change so that the trees can be further aligned. We would continue this process until the roots of the trees become equivalent. Therefore, we arrive at our final algorithm. First, we roll back the execution to a non-equivalent point, and then we change the faulty node to its equivalent version, and then we roll forward the execution to align the trees. We would repeat this process until the trees are completely aligned, and we would output the changes we have made. In our previous example, after replacing the faulty fluent tree to the correct version, we would then roll forward the execution and find that the packets are now received by the same next hop. And we would output the accumulated changes, which is a change to the fluent tree, as the result. Now that I've told you how differential provenance works, let me show you some result we got with differential provenance. We implemented our debugger called diffprof, mostly for network data log programs, but it also works for NetCore programs, and it is applicable beyond SDM programs. For instance, it works for Hadoop MapReduce as well. And in our evaluation, we asked several questions, and indeed we answered all of them in our paper. But due to time limitation, I will focus on 3 questions in my talk. How well can differential provenance find the root cause? How quickly can it do so? And how well can it work for complex networks? To this end, we adapted 7 diagnostic scenarios, mostly from existing papers. Some of the scenarios are adapted from our communication with industry collaborators. And our baseline is a provenance-based debugger that does not have reference event support. For the running example that you saw earlier, what we found is that basic provenance returns more than 200 vertices on the symptom provenance tree. And the provenance tree for the reference event is also more than 100 nodes. What we found is that the naive diff has 278 nodes, but differential provenance is able to pinpoint a single node as the root cause, and that corresponds exactly to the misconfigured routing entry. You might wonder whether this is just a coincidence, but in fact, we tried diffprof on the other scenarios you just saw, and we found similar results. For the scenarios that we tried, the reference and symptom provenance trees are quite complex. And the plain tree diff is not significantly simpler. In fact, sometimes they are even larger. But differential provenance is able to pinpoint the one or two problems that correspond exactly to the root cause of the problem. Next, we ask, how long does diffprof take to find the root cause of the problem? We can see that for different scenarios, diffprof find the answers with a different amount of time. But for most of those queries, it returns an answer within 1 minute, which is already a lot faster than if you have to manually examine the provenance trees and find the root cause. And I should also say that we did not try very hard to optimize diffprof for speed specifically. Next, we ask the question, how well does diffprof work for complex networks? To answer this question, we set up a larger topology with complex configurations and heavy background interference. We replicated one of the forwarding errors in paper ATPG, and we injected multiple other faults just to create even more interference. And we injected a mix of background traffic by live applications and a packet replay. What we found is that differential provenance is still able to pinpoint the single faulty entry to be the root cause of the problem, despite the heavy interference. This might look surprising, but in fact, diffprof can do this because it leverages provenance, which captures causality, not just correlations. In other words, it doesn't simply return any difference that it can find in the network, but only the differences that are causally related. So to summarize, network debugging is not easy, so we need a good debugger to find the root cause of our problem. Our key insight is that oftentimes we have more information than we are using. We can use reference events and think about the differences between the bad symptom and the reference event. This is what we call differential provenance. We built a debugger that works for SDNs, but is also applicable beyond SDNs, for instance, to MapReduce and other distributed systems. And we found that differential provenance is able to deliver very precise diagnostics as a result. Thank you. found is correspond to the actual number of misconfigurations in the network, not the reference event. For instance, we found one or two misconfigurations because in the problems that we recreated from other papers, the scenarios themselves contain one or two misconfigurations, and that is why diffprof found those one or two nodes as a result.
Thank you. Once again, beautiful work. Thank you.
Thanks.
Hi, interesting work. I'm Apur from TU Berlin. I have one question, like what kinds of faults can you figure out? Like you mentioned ATPG, and ATPG can only figure out the match faults, the action faults, not the match faults. Like for example, a header is matching a rule which is not supposed to match, right?
Right.
So how do you detect those anomalies? Or do you, I mean, what is the coverage of the rules in all of the switches in the network? That's what I want to know.
Right. You mentioned ATPG. One difference between our work and ATPG is that we do not focus specifically on the data plane, so we can handle more general cases than ATPG. For instance, it could be applicable to general distributed systems such as MapReduce. But that said, diffprof works when there is a reference event. So that is one restriction on the kind of faults that diffprof could handle. Beyond that, diffprof mostly works for functional faults, not timing faults such as race conditions, where the computation result is correct, but the timing perhaps is delayed or something. Diffprof does not work well for that kind of faults, but we are having an ongoing research project on those kind of faults as well.
Okay, thank you.
Okay, thank you, Ang. I think we have used up our questions, and I think one of